out of sound. I have to have it here. I cannot mute it. So the recording is on. Echo 360 is on. I think we're ready. This room still has certain technical difficulties, which is fine. It's not about having a perfect system. It's impossible. Every technical system might fail. That's natural, like make a mistake. But that is why we always have to have a backup. And now I do have a, I think, more or less workable backup. And again, call me or just use Zoom to speak out, because I can hear what you say on Zoom. I posted a file about a day ago, and I had only one suggestion so far. And the good thing is that's exactly what I want to talk about today and even tomorrow. So if I will cover this, maybe we don't even need an extra lecture. If I get more topics, in that case, yes, I have no problem to create a video. And tomorrow, if everything goes according to plan, I would like to set aside any questions. If everything is absolutely clear for everybody, in that case, I just will have to start a new topic, something simple at the beginning, because we can't just lose time, especially now. All right, a quick review. This slide demonstrates general processes happening inside of a simple circuit with one active element and one passive element. And active element or battery is just a source of fixed potential difference between two electrodes with a high potential, with a low potential. We always can set the low potential to 0 and measure all potentials relative to that. And potential difference or voltage, well, depends, because difference has to be calculated between two potentials. It's up to us to choose the point number 1, the point number 2, measure or calculate potential number 2, and subtract. And as we know, because we did yesterday, a wire has no resistance, and that means it does not change potential. The Ohm's law says that. No resistance, R is equal to 0, potential difference. Choose. If anyone types anything in chat, I will read it. No? Okay. And these are the rules. What do we do about the rules? Memorize and practice. And the junction rule is basically a law of conservation of charge. Charge cannot disappear. Charge cannot be created from thin air. So if charges split, total amount remains the same as before or comes back. And when we have several elements connected one after another, potential difference here plus potential difference here gives potential difference in the ends. And what does it mean? It means voltage 1 plus voltage 2, maybe 3, will be equal to the whole voltage. And for elements connected to parallel, they all share the same voltage. That's it. These are the rules. This is all we need to remember. And we also know that electric current does work. You know, that when electrons collide with atoms, ions, nuclei, they transfer a certain amount of energy before collision, more energy is being transferred, and the atoms start moving, wobbling, oscillating faster and faster, and that leads to temperature rise. And we use it in different forms. And well, a question to you. And I'm going to check what is happening on the website. I have a hope that everyone will answer this question correctly. Hope is not a belief. And an experiment makes a difference between hope and a belief. And this is an experiment. I have a hope, and now the experiment will tell me, well, one student so far answered the question. One is not an option, you know that. Now, if Echo 360 works fine, you can see everything and hear everything. In that case, I can't create breakout rooms that would recording. All right. So you can leave Zoom and stick to Echo 360, viewing and listening to it, unless you have an urgent feeling sometimes to chat to someone or to me. But in that case, you can always join the meeting again and say something or write something. All right, so my hope was crashed. What does this Q mean? Yes. That's heat. That's the amount of heat, and heat changes with the temperature. And this is charge, and charge over time is electric current. And when we write an equation, we need to know the exact meaning of exact variable, of each variable. Otherwise, we make a mistake. So temperature, time. Well, electric current does work. How can we calculate it? Very simple, actually. Because let's say we've got a wire. We look inside it, we see, again, for simplicity, fictional positive charges traveling, let's say, to the right. So this is the direction of electric current. We know that for a charge, for one charge, the work done by electric field on that charge equals the charge times delta V of magnitude. Technically, to get used to this, technically, V initial minus V final. So if I want to calculate total work, all I need to do is calculate the sum of work done by all charges. And that will give me total charge potential difference. That's it. That's work. And of course, if I want to calculate something simple like power is work done by every second. So a charge over, what is the meaning of this? Yes, time curve. So this is how we can calculate work. And this is the original expression for electric power. Power is work done every second. But again, because we can use the Ohm's law, we can write two more expressions for electric power. And if you calculate the power, multiply by time, you can calculate work. For example, in this problem, which we already have solved, if you want to calculate energy it produces, that energy should be equal to the amount of work done by electric current, and that should be equal to current times voltage times, well, this is power again, so power times time, work, and we know electric current was equal to 0.4, and we know in this situation we have two batteries, so the voltage is 3, and time is 10 seconds, done. So 12 joules of work is done. Very simple. So now we're just adding one more expression to the bottom of this list of the rules. Again, what do we do about rules? Memorize them. Well, let's practice, and we're going to trace potential, and we're going to use rules for combining resistors, and we're not going to learn anything new from this point forward. From this moment, nothing new, actually. We have learned all relevant related theory. Well, battery. What does the battery do? Provides a fixed amount of, we call it EF. And this is the voltage between these two electrons. This is a potential we could set to 0 because it's lower, and this is potential we set to 12. And now we know that a wire does not change electric potential. So starting from this instant or moment or location, we can say that along this wire, potential does not change. Again, for a moment, why? Well, I can choose 2 points here. Let's make points A, B, D, E, and that's going to be F. You see, I choose point where something ends or begins. Battery ends, wire begins, resistor ends, wire ends, resistor begins. So in a closed circuit, the same point is always a last for something, but first for something else. So electric potential phi of F or phi, people call it differently in British, L, F, right? So the potential F equals 0. Why? Again, I set it to 0. I set it to a different value. Yes, would it make a difference? No, because remember, all our important equations has potential difference. So if I change the reference point, it does not change the difference. So that's why it's a good flexibility to use. Set one potential to 0. Now, potential A will, well, F plus EMF. that will be equal to, all right, 0 plus 12, 12. Potential B, now you should tell me the value for this. Well, don't call, just say it to your screen, I will fill you. The rule says the wire does not change potential. And again, I said why, and this is why electric potential difference and A. Should be equal to electric current, well, technically from A to B, times the resistance of this circuit between points A and B. But this resistance is 0. Is the resistance less? That is why VB is equal to VA, or 12 volts. What is happening next? Well, that depends. This element, resistor, number 1, 6 ohms. Has a potential difference which might be equal to 0 or not. When would it be equal to 0? Well, again, we could apply the Ohm's law. The Ohm's law says, first of all, if electric current travels, it should travel from high to low, from high to low. So electric potential B minus VC should be equal to electric current. Now, I know that electric current has to be the same everywhere, so I don't use any subscripts, times the resistance, number 1. Is it equal to 0 now? No, because now neither R nor electric current are zeros. Now, we don't know the value of this current, but we know it exists, because in a circuit, closed circuit, there has to be electric current traveling through it. So, not 0, but what? Well, I don't know why, okay, but I know R6. That's all I can write right now. All right, moving on. This actually tells me how I could calculate electric potential at point C. It would be equal to electric potential at point B minus I times 6. Or, because I know electric potential at point B equals 12, 12 minus I times 6. Okay. And that's all I can do for now. But I can move further. And what does it mean? It means I can make a statement about the next potential. The next potential is D. All right. D is the end of what? D is the end of wire. The wire has no resistance, does not change potential, so equals to C. Okay, nothing new. Now what is happening? There is electric current traveling through the second resistor. Electric potential drops, decreases in the direction of electric current. So I can fit one more picture here. R2, potential D, potential D. And I know that electric potential D will be higher than D. And I know that according to Ohm's law, the difference will be equal to same current times new resistance. Well, what else do I know? I know that if I calculate voltage, number 1, and if I calculate voltage number 2, and I add them up together, I should get the original initial voltage of 12 volts. So now I've got a system of equations. 1, 2, 3, 4. And what can I do? I can solve that. And the result will be, of course, what? Well, we've done it yesterday, so we can repeat it very quickly. Because I have this battery of 12 volts, and these two resistors connected in series, I can replace them with only one resistor. This single resistor are equivalent, should be equal to just this plus this equals 9 ohms. So now what can I do? I can just calculate the electric current immediately. Electric current should be equal to, well, technically electric current should be equal to this voltage, delta V, divided by total resistance. But we know this voltage is equal to 12 over 9. 4 over 3 amps. And now what can I do? Well, now I can go back to the original circuit. I know the current now. And if I want to, I can calculate the voltage number 1, for example, because the voltage number 1 will be equal to now electric current times resistance number 1. Technically, keep in mind, I should have written this, because all elements in this equation must be related to the same element. But I know that the electric current in this circuit is the same everywhere. So I can calculate that voltage. It's 4 over 3 times 6, which gives me 8 volts. And automatically, voltage number 2 will be equal to this. Calculate your nodes. You know what? There are people still in Zoom, so please, some of Zoom people, type in chat the answer to the voltage number 2. Also, should we have finished it already? I have less and less people in Zoom. 4, thank you. That is exactly right. And how could we find it? Well, 2 options. Number 1, 12 minus delta V 1, or number 2, current times R2. The answer is, well, 2 times 2. Twelve minus 8, 4, and 4, 3, yes, 4. Anyway, 4 volts. So, of course, no matter how we do it. Now, there is one more interesting and very handy sometimes information. All right, so the screen. And now I need to actually first erase everything. All right, I'll do this for now. So 6 ohms. 3 ohms, 8 volts, 4 volts. Do you see any similarity? Electric current is the same. Electric current is the same. And you can see that if you have an element with twice more resistance, the voltage across this element twice higher. 6 is twice larger than 3, and 8 is twice larger than 4. Of course, this is just a standard logical consequence of, well, the fact that electric current is the same. So I equals, on one hand, delta V1 over R1, but on another hand, delta V2 on R2. So in order to keep electric current the same, if you double the resistance, you have to double the voltage. This sometimes comes very handy. Saves time. And what else can we calculate? Well, energy power, for example, the power dissipated by the first element will be equal to, again, current times voltage number 1. The power for the second element equals same current times the voltage number 2. If I want to calculate total power, that will be the sum. And what is it equal to? Well, this is how much work every second the battery does. Energy doesn't come from anything. So this will be the power of the battery. And the calculations. Now, of course, we need to move on to the next easiest situation. Parallel wiring, parallel. So first we need to redraw the circuit. You always can redraw the circuit. Wires are flexible. We can imagine that we flex the wires in any way we like. So what I have? Battery, power source 6 volts. Then I've got one resistor. A speaker is a resistor, a device. Also call it a load. It's loaded. R1 equals 8 ohms. Are we done? No. This is just this part. I have a different part. Right here, I've got a junction, and a wire goes away and then goes through a second resistor. It does not touch the same wire. It goes above or below it, and then it touches another wire. So this is point A in my circuit, this is point A, this is point B in my circuit, this is point B. And I just got a wire that goes to another resistor and comes back. And that's it, that's R2, which is equal to 4 ohms. Now, the analyzed potential is a very simple action here. We set this potential to 0. This potential V plus will be equal to 0 plus 6 volts. And also potential here is the same as 6. And potential here is the same as 0. So for all of them, voltage equals 6. What about electric current? Electric current, of course, different. Electric current, which goes out of the battery, I, splits here and there. So I1, I2. Of course, immediately we can write the junction rule. Do we need to use it? Well, if we have to calculate everything, yes. What could we calculate right now? Every current. current number 1 will be equal to delta V over R1, which is 6 over 8. 2 and 2, 3 over 4. Yeah. Current number 2 is equal to same delta V over R2, which is 6 over 4, which is 1.5. Yeah. 3 over 2 amps. And now, of course, we can calculate total current. Where does it travel? Well, this current travels through the battery. So it's going to be 3 over 4 plus 6 over 4, 9 over 4 amps. If I made a mistake, just say something on Zoom. And of course, we can just apply an equation for powers and calculate any power. I'm not going to do that. All right, I just write it down. The power equals current times voltage. Of course, for the sake of exercise, you can use other equations and calculate the power as current squared times resistance or voltage squared divided by resistance. You should get the same result. And okay, this is done. Language. So technically, in this particular problem, we don't use a standard battery as a power source. We use something with this symbol, a wave. It means a generator. We'll talk about generators soon after the exam. It means the voltage actually changes in time, oscillates, like in every power outlet. However, we could always use some kind of an equivalent average value, and that equivalent value has a name RMS, which means root mean square. Y doesn't care. We just need to know this is just a fixed value we could use to represent a generator. That's it. Just in case you will need this word on the website. Question? And while you're answering this question, I'm going to prepare the demonstration, actually several demonstrations. But first, tell me what you think. You see two different circuits, and each circuit has exactly the same battery, and each circuit has bulb or bulbs that also are identical. So if you would look at this circuit, which would be brighter, this bulb or this bulb? Okay. Hello?
Hi, I just wanted to let you know that the camera on Zoom, one of them, are like pointed into the Zoom. I don't know if you need that.
On Zoom?
No, on Echo 360. So we can see everything fine, it's just that it's pointed towards the ceiling, the one that you would use to show the demonstration.
Okay, but the screen that used to be black now is fine. You can see everything on the screen, correct?
Yeah, everything is good.
Thank you very much. Okay, that means I will have to switch to. Shoot. How about now?
No, it has to be a big move.
Really? Because for me it is moved actually.
Oh, okay, there we go.
Oh, that's good. That's actually my fault. I forgot to do it in the morning. Shit. If anything is weird, please tell me as soon as possible. That could have been fixed 35 minutes ago. With all this stuff, sometimes I just lose my attention, you know that, I make mistakes. All right, thank you.
No problem.
All right, and actually, I'm still going to switch to document camera. That's a good point. And since I'm doing this, I'm going to show this. Switch to YouTube. This. Don't forget to switch it back. It's juggling. So by now you should have answered the question, and I will check it later. But let's see what's going to happen. Zoom camera. Now I need to, because I'm also making video for Zoom, I need to a good thing I have long hands. All right. What do I need? Devices and wires. Simple circuit. Just two devices and two wires. This is how bright it is. Now I need, how many wires do we need now? 1, 2, 3. I need to complete the circuit. Take 3 wires. 1, 2. Take this and the moment of truth. Clearly dimmer, no matter how you look at it, dimmer. And that is actually absolutely natural, because by adding an extra element in series, we are increasing total resistance with the same voltage. That means we have to decrease the current, actually in half. Or we can say that now, because these are identical, this voltage plus this voltage should be equal to original voltage. But same voltage and same voltage, that makes it a half of the voltage of the battery. So if I drop the current or the voltage, or both, the power, of course, drops as well. And that's what we observe. The brightness is directly related to power. That's what we need to remember. More power produced by electric current, more work done every second, brighter bulb, less power, dimmer bulb. And now I'm gonna, so look at the screen. I'm gonna keep this camera for now. Oops, wrong. All right. So just very quickly in equations. What I need is power. Power number 1 equals current number 1 times voltage number 1. Number 2, power number 2 equals current number 2 times voltage number 2. At this point, I don't even think about how to calculate. I know they have to be related to the same element. So if this is the element number 1, 1, 1, 1, the element number 2, 2, 2, 2. Now I can start thinking, okay, this is, well, this is, well, the power. For the first element, I just keep it here. What am I have? This voltage, delta V battery, should be equal to delta V1, because that's the same battery. What about electric current number 2? Well, electric current number 2 should be equal to, well, we know it has to be equal to a half of the voltage of the battery times the same resistance. The resistance is the same because it's identical, it's the same battery. It's important to read with attention. Now, you can ask again, why is it a half? Well, as I said, this has to split between two identical bulbs. So delta V2 times 2 should be equal to delta V1, which is the battery. We need to do this to be as accurate as possible. All right. So now I can calculate power number 2. The power number 2 will be equal to what? Current times the voltage. Well, now we need to compare, right? How would I do that? Well, what they have in common is the battery. So I need to rewrite this equation also in terms of voltage. And current equals, hello? Yes, you're right. Now you can see it. I'm gonna wait a minute to process what happened. I have to switch back. That's why I need someone here who would tell me constantly, Mr. Ryu, you forgot to switch. All right. So what I said, power number 1, power number 2, and I'm calculating power for each bulb individually. And here right now, I need to finish the calculation. I just need to apply the Ohm's law. One more time. Times delta V again. So what do I have here? Power number 1, R times delta V1 squared. When I square it, I don't need to use vertical bars. And what do I have for power number 2? 1/4 of the same. I just said that. 1/4 of the same. Well, this is an example of the strategy. Now use this strategy to answer this question, please. So please take a mental picture or an actual screenshot of this picture, because now I'm going to switch to camera again. Okay. Well, now I have the circuit number 1 the same as before. What do I do differently? Instead of connecting these bulbs in series, now I am connecting them in parallel. Actually, now I want to use a stronger battery. 9 volts. This is something you really missing because of the virus. You would have to do all this in a lab, which is kind of fun to do. Again, 12 years ago or so, I've been offering to prepare some kind of a kit that could be sent out to students. No one thought it would be useful. For now, of course, everything is the same. Same battery, same bulb, identical, same brightness. Now I'm gonna connect. Well, so far nothing, yeah. I need another wire and I have to plug it in. And what do you expect? Well, that's another web sign. I'm gonna give you a little bit more time to think it through, and I'm gonna check what's happening on the web sign. You don't see it, you don't need it, you see? This is equation number 4. And we've got circuit 1, circuit 2. Which is brighter? This, that, same? We've got a distribution. The winning answer is number 3. And the winning answer now is correct. See? But adding this in parallel does not affect this brightness. Why? Well, because when elements connected in parallel, the voltage is equal to the voltage of the source of the battery. Same voltage, same bulb, same current, same power. We only have to be careful with saying words like same current, same power, because there's a specific important assumption. The same current, you should ask where? And I can say electric current through this bulb is the same as electric current through this bulb. And that is correct. We'll do some math very quickly. But if I ask you, is electric current through this battery the same as electric current through this battery? You should say no. Because now this battery actually should supply twice higher current, because it should travel same here and, which means plus in mathematics, and the same here. So electric current in each bulb 1, 2, 3 is the same, but electric current supplied by the battery here is different. All right. Plus, some of you have done the lab yesterday, and this is kind of one of the questions you should have answered. So what do we do now? I want to move this away. We couldn't obstruct. We need to check. Okay, moving on. So, what do we have to write? Here, EMF, resistance, current, electric current equals EMF, which is voltage over battery over R. What do we have to write here? Well, EMF, all right, current, all right, resistance, resistance. But now I have to recognize the existence of a very important element, junction splitting point. So this electric current must split between two. However, each individual electric current still will be equal to the same EMF over the same resistance. That is why the brightness is the same. Well, measuring things, it's important to know how to measure things. So for that, I'm going to use another card. I have to switch again to You don't need to see it. Zoom out. Back. This is why I need a work study student. So, measure. Well, I'm going to use just to show how they work a standard decayed resistor. I can change the resistance by moving these dials, knobs. Right now it's 100 ohms. I need a power supply. I have to connect it. And turn it on. Okay. First, I need to use my wires to connect the power supply. It's like a battery, plus, minus, to this resistor. And I have to complete the circuit, of course. Well, now I can turn it on. There is some voltage here, about 30 volts. No bulbs, you cannot see anything. Well, you can see the measurement, but now I can use a specific device that can provide the value of that voltage. Of course, I have to plug it in. Turn it on. Now I need two electrodes. How do I measure voltage? Well, voltage is potential difference between potentials at two locations. So you need two wires, of course. And now I can measure potential difference between electric potential at one point and electric potential at another point. I just have to connect, touch them, and I read the number. 30 is more than the limit. Okay, 28. That's it. What's going to happen if I switch them? Well, I see the same magnitude but opposite. Why? Well, because by default, when I measure voltage by any device, the red represents higher potential. And if I connect a red to a higher potential and a black to a lower potential, the number is positive. If I see a negative number, it means I connected it vice versa. So now the red is connected to a lower potential and black to a higher. Easy fix, just switch them back, right? Done. Okay. How can I measure electric current? For that, I need a different device. Why cannot use this one? Okay. Used to be measuring electric current, now it's not. It's old. Okay, so what we have a new one. These things are actually really expensive. And now, how do I measure electric current? I'll turn it on. What is electric current? Electric current basically proportional to number of electrons traveling every second through a wire. So we need a counter. We need someone, a tiny demon, counting those electrons, first, second, third, fourth, and then multiply by the charge of electron. And for that, electrons should travel through the device, and counter will be counting. Well, how can we make it? Well, we have to break the circuit and make charges traveling through the device. Why nothing is on the screen? Well, because the circuit now it's broken. It's not complete. I still have to connect the power supply back to the circuit. That I use a longer wire. What does it mean? Electric current now is higher than the limit. So where is it? Yep. And why is it a minus? Same thing. How does electric current travel? From plus, this is plus, eventually to minus. And here, this red high current terminal is connected to low. How do I fix it? Flip. So 277 milliamps. And what's going to happen if I double the resistance? Now you can see the voltage and electric current, and I am doubling the resistance. What happened to voltage? Nothing. The same voltage. Electric current drops in half from 28 to 14. This is how Ohm's law works. And of course, just 100 and another 100 in series. What happened to electric current? Of course, it's a half of the previous 14. I just doubled the resistance differently. What about voltage? Well, now, if I measure voltage across the whole system, it should be equal to the voltage provided by this supply, which is, what is it, 28 as it was. But because I have 100 and 100 same resistance, that voltage now splits evenly. So I should have 14 and 14. All right. Now you know how to measure things, right? Now you actually could teach how to measure things. What is the most important action for me after this experiment? Don't forget to switch everything back. I'm going to do this later. So camera goes back. Presentation. So this is how we measure things: electric current, electric potential difference, voltage, electric current. Question to you. Yeah, I guess I need to bring them back. Well, only one good thing. I'm going to use a smaller version. So it is a question to you. I'm going to prepare the circuit first. All I need is one battery, one resistor, and one switch. One battery, one resistor, one switch. And I will have to do what? Connect battery to the bulb. Network is now to the switch. The switch is open. And now one more wire. The switch is open. Electrons cannot. That's why the bulb is off. The question here is, if I use this device, I will show you in a minute, and I want to measure potential difference or voltage, well, what will I see? I want to test if the device is actually working. I'm giving you time to answer this question. Okay. Now we can switch. Again, sure. So, now, I'm just giving you time to process the question, to answer correctly. Okay. You can read the numbers, everything. So first, this is just a 9-volt battery. Do you work now? Come back, old friend. Yes. Where can I measure voltage in this circuit? Anywhere I like. I can measure the voltage. Across the battery. 9 volts. I can measure the voltage across this yellow wire. What do you expect? No electric current, no resistance. Should be no voltage. What we need to measure is the voltage across the switch. So between these two plates, electrodes, number 1, number 2, the moment of truth. Nine. And all you need to do is to analyze the potential, trace the potential, electric potential. And what is voltage? Potential difference. So let's trace it here. You read a plus, you read a minus, and you read 9 volts. So this battery provides potential difference of 9. But electric potential of a minus electrode, we can set to 0. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. In general, a bulb might change electric potential, but only if electric current is not zero. There is no electric current, it's open. No current, that means current times resistance 0 times R equals 0. Potential difference is 0. Potential does not change here. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, what about this potential? Well, this potential should be equal to potential here, 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 here. And this is 9. So potential here is 0, potential here is 9. Potential difference, 9 minus 0, 9. And now I have a question. What's going to happen if I close the switch? Well, now electric current, of course, is not 0. We can see it, literally. Now, what's going to happen to potential? Well, let's think. Still 0, still 0, green one, still 9. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. But now potential has to drop, has to change. To what? Well, okay. 9 plus 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9. What is happening here? Nothing. A closed switch acts like a wire, has no resistance, does not change potential. So 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9. Potential here is 0. Potential here is 9. Potential difference of voltage is 9 volts. 9 volts divided by resistance, 6 ohms or something like that, gives you current. Now, if I want to measure voltage across the closed switch, what do you expect? Just one moment. I'm going to do this later. Question number 6. Question number 6 to everybody. I will measure the voltage. I will measure the voltage across the closed switch. You need to enter the answer to this question right now. Everything is the same. I don't touch anything. I just measure the voltage between these 2 points. First electrode, second electrode. Nothing. There is no voltage, and it shouldn't be. I just said 0, 0, 0, 0, 0, 0. What was this? This was 0, 0, 0, 0, 0, 0, 0, 0, 0. 9, 9, 9, 9, 9, 9, 9. 9, 9, 9, 9, 9, 9, 9. So 9, 9, 9 minus 9, 0. All right. I want to show you another experiment, not related to voltage directly, but related to energy conservation. I want to add this capacitor in the circuit, and I want to see how those fictional positive charges, positrons, would move. So the switch is open, and you can kind of try to make a prediction for yourself. What's going to happen? What will you see when I complete the circuit and I will close the switch? This. Nothing yet, of course. It's not open. This. I mean, it's not closed, it's open. Sorry. This. This. Still nothing. Of course, the switch is still open. I need to close the switch. Let's close the switch. Electric current travels through the bulb, electric current travels through the switch, electric current travels through the battery, and evidently electric current travels through the capacitor. What is happening to the capacitor? It is charging. And this will take too much time for this battery. I just want to take a smaller, it's 6 volts, we know. And now it's not enough. Why? Well, let's discharge the capacitor like we did it for electroscopes. See, the bulb is on, electrons run, positrons run, but the bulb is getting dimmer and dimmer and dimmer and dimmer. And right now, the bulb is off. And you can see those dots move slower and slower and slower. Why? Well, the batteries, of course, supply the energy. We can calculate the power if we knew electric current. But what is happening to that energy? Energy now is split between the bulb and the capacitor. And capacitor is charging. Slowly, slowly, it takes more and more and more energy. And the capacitor has a fixed amount of capacitance. This is 1 farad capacitor, very high capacitance. But even this capacitor eventually will be filled completely. And when it will be filled completely, electrons will not be able to move. That is why we observe slower and slower motion. Because eventually, well, capacitor is completely filled. There will be no motion anymore. Electrons will stuck and electric current will stop. Right now, electric current is not 0 yet, but still much lower than required for this bulb. It takes time to fill up this large capacitor, but eventually they will stop. I'm not going to wait for that. I'm going to show you what happened to energy. Where is the energy now? Here in the capacitor. Capacitor has stored amount of energy. What amount? Well, you know, 6 volts, 1 farad. You can calculate. Now I want to remove the battery, connect the circuit. Switch is open so far. And now I want to close the circuit again. See what's happening. What is happening now? Clearly, there is a source of energy in the circuit. What is that source? Now it's a capacitor. Now capacitor gives away the energy it previously stored from this battery. And of course, that energy eventually disappears, dissipates, being transferred into heat and light. And of course, if we wait long enough, this bulb becomes dark again and the charges stop moving. This is an example of energy transition inside electrical circuits. All right, I'm gonna let it stop eventually. All right. Equations. Equations. So we've answered 6 questions. So this was, again, a question about potential difference across the open switch. So in this circuit, not in mine, in this circuit, this potential could be set to 0. This potential automatically becomes 12 volts. And here we will have 0, 0, 0, 0, 0, 0. This potential is 0. And here we'll have 12, 12, 12. Now this delta V is equal to electric current times resistance. But there is no current. This switch is open. That means delta V is equal to 0. That means potential does not change. So 12, 12, 12, 12, 12, 12. So this potential is 12 volts, 0 volts. And the potential difference across the switch, 12 minus 0, 12. That's in my example, the answer is 12. In my experiment, the answer was 9. And here, well, we just did it. Now there is no resistance here. And if electric current is not 0, doesn't matter. The potential difference between the ends of a switch should be equal to I times 0, 0. Not a question on the other side. Just quickly analyze what's going to happen. Electric circuit, okay. Bulb number 1 has a resistance of R. Bulb number 2 has twice more resistance. Well, the question is about current. So we have to make a conclusion about the connection. And when we have elements, it could be series, parallel, or neither. We need to know when it's in series, when it's parallel, or neither. Clearly here, the electric current has to be the same. That's the answer, the same everywhere. And electric current, and electric current, and electric current, and electric current, I. Okay, because it's in series. What is different? Voltage. This voltage, delta V1, is across a resistor, which has a resistance a half of the second. This element has twice more resistance, so this voltage V will be twice of the voltage number 1. And if we add them up together, the voltage number 1, the voltage number 2, that should be the total voltage in the circuit, or we call it EMF of the battery. So I could say immediately now from this reasoning that the battery should have 3 times the voltage number 1 value. Or the voltage number 1 is 1/3 of the battery. And this everything is based on our knowledge that the current is the same. Another example, this diagram actually helpful to kind of visualize what is happening to electric potential. Electric potential in a way is similar to gravitational potential energy of 1 kilogram. When potential rises, it's like lifting up that kilogram, but moving. And then when potential drops, decreases, it's like sliding down on a slope. So what we have here is the battery only one battery so far. Tomorrow we'll talk about two. One battery with a negative electrode and a positive electrode. And we are setting, of course, electric potential of a negative electrode to 0. That's actually symbol for grounding. Every actual circuit has grounding. There's a wire that basically somewhere gets in the ground. Why? Well, because the Earth is a huge capacitor, so huge capacitor that it can basically absorb any amount of charge and doesn't change its potential. So the electric potential of the Earth we could always treat zero as zero. So we ground it to make it zero. But what does battery do? The battery raises the potential by the value of EMF. And what is happening next? Because this is a closed circuit, electric current is not zero. And when electric current traveling through a resistor, potential drops. But then, because wire does not change potential, potential remains the same until new resistor begins. And then potential drops again. And then it remains again constant. And now we know what to do. We can solve this problem. We just need to redraw the circuit in a more convenient way. So battery, well, first resistor, second resistor, back. This potential is grounded, 0. This potential automatically becomes equal to, we need to find it, equal to a question mark. Okay. This is electric potential. What do we know? Well, we know that electric current travels outside of the battery from high potential to low potential. That's electric current. And now I need to make a very important note about the terminology. Electric current has a direction, and sometimes we need to describe that direction. Question is, what is the direction of electric current? This question has no answer unless you say where. And in this situation, we have several options. We can ask, what is the direction of electric current through the battery? What is the direction of electric current through the first resistor? What is the direction of electric current through the second resistor? And there's also a question, what is the direction of electric current in the circuit? These 4 questions have 4 different answers. Well, first of all, if you look at the circuit, this is this direction has a name, clockwise. So the direction of electric current in the circuit is clockwise. All right. But for each individual element, electric current through the battery travels How do we say it? To the left. Electric current through the first resistor travels, how do we say it? Up. Electric current through the second resistor travels, how do we say it? To the right. So keep it in mind. Now, potential. Well, so we have no this potential, but we know until this place it remains the same. So this is V plus. And because electric current is not zero, all right, as I said, electric current in the circuit is clockwise, electric current through the battery is to the right, electric current through the first resistor is up, and electric current through the second resistor is to the right. And electric current through the battery is to the left. And electric potential drops to new value, let's call it V1. And V plus minus V1 has to be equal to electric current times resistance, which is 0.1 times 10. But then potential drops to a new value, and this new value is just equal to 0. So now V1 minus 0 should be equal to electric current times R2, which is same current times new resistance. And now, well, this is what I'm looking for. And that will be equal to what? 0.1 times 10 plus V1 or 1 plus 2 3 volts. All right, that's it for today. And thank you very much. Have a nice day. Hopefully tomorrow we will come back completely to the original system. Don't forget, lab 2 is today for other sections. And I have my office hours later in a day. Thank you and goodbye.